Hello and welcome to a session on clean architecture. Today, what I'm going to talk about is what is clean architecture, what are the various layers that form the clean architecture, what is the purpose of each layer, which components come under which layer of the clean architecture. Then we'll also see how clean architecture can be implemented in Android. And lastly, we'll cover the principles that we need to follow in order to achieve clean architecture. So firstly, I would like to take you through the visual representation of this architecture. So as you can see in the clean architecture diagram below, there are four layers in the clean architecture. The outermost layer is called the frameworks and drivers layer. It comprises of the web or the web interfaces. It comprises of the UI, the external interfaces, the database, the devices from which you get input or give output to. Then the layer just beneath is the interface and adapters layer, which comprises of controllers, gateways, and presenters. The layer beneath that is the use cases layer or the application business rules layer. And the one in the center is the enterprise business rules layer, which comprises of entities. And the clean architecture is designed in a way that the source code dependencies can only point inwards. So what that means is nothing in an inner circle can know anything at all about something in an outer circle. Now the reason behind that is the outermost layer of the clean architecture comprises of all those components which are most likely to change with passage of time. Now by that what I mean is, for example, with passage of time you might want to renovate the UI of your application, which is most common thing to do, or you could maybe want to add or remove or change the APIs from where you are actually getting data, or you might want to say change the DB which you are using. For example, let's say currently you are using say Cassandra, and tomorrow probably you think that probably a SQLite could be the one which you want to go for. So all these things are more likely to change than any of the internal layer entities. So in the clean architecture, the further in you go, the higher level the software becomes. The outer circles are mechanisms and the inner circles represent the policies. Now let's go through each and every layer, starting from the layer in the center, which comprises of entities or the enterprise business rules layer. So entities, in case of a single application, as in case of Android, they are the business objects of the application. Entities encapsulate the most general and high level rules. So these business objects kind of contain the core logic of the application, and they are least likely to change when something external changes. Now, the advantage of keeping something like entities at the center is these are the most stable throughout the life of the application. And the way the dependencies are arranged is if there is something in the entities that changes, it will cause a ripple effect and would affect all the layers above it. Now, since this is where the most stable components reside, so the chances of them changing is very rare, and hence this becomes this makes this application or the architecture more maintainable. Then we talk about the use cases, which is the application business rules layer. Use case layer covers all the use cases with respect to applications that the user wishes to do on entities. Now let's take an example. For example, let's say there is a financial application and it consists of a say business object called a bank account. Now there could be several use cases with respect to a bank account, and these could be, say for example, we might want to take out some money, or we might want to deposit the money, or we might want to know the current status of the amount of money that is there in the account. So all these things, these three would actually become the use cases for the business object, that is bank account. Use cases orchestrate the flow of data to and from the entities and direct those entities to use their enterprise-wide business rules to achieve the goals of the use case. Now we will talk about the next layer, which is the interfaces and adapters layers, and also called the gateways, presenters, and controllers layer. The main reason of having this layer is this layer helps in converting data formats between the innermost layers, which is the layers comprising of use cases and entities, and the outermost layer, which comprises of DB, UI, and stuff like that. The outermost layer comprises of the tools, is called the tools frameworks layer, and this layer consists of databases, web, UI, and frameworks. So this is where the details of the system are, and this is the most concrete layer, whereas entities form the most abstract layer. Now let's talk about how this architecture is implemented in Android. So if you look at the right hand side diagram, the innermost circle consists of domain, which comprises of the entities and use cases from the clean architecture. Then outside that come the view models and repository. Presenters also come in this layer. And the outermost layer consists of UI, DB, and web. And the way it is implemented is we usually form different modules in Android. So the most independent module is the domain module, which comprises of the use cases and entities, as shown by the blue and the brown boxes. Then above that is the presentation and data layers or modules. In the presentation modules, we have presenter and UI. And in the data module, we have repositories and WebDB. Presentation has a responsibility that whatever data is represented by domain or entities, it should could be displayed. And the main responsibility of data layer is to actually get this data from external resources or from databases. Now let's talk about how the flow is between all these layers. So the flow is like the user will perform some action in the UI layer. For example, let's say he might want to check, open and try to see the details of the account. This might trigger some change in view models, and that might lead to an action in the domain use case layer. The domain use case layer might want to extract the details that the user have extracted has requested, and for that it might go to the repository layer. The repository layer will actually fetch it from the data source and give it back to the domain layer, and that would actually reflect back into the view model. And since UI is observing the view model, any changes in the view model data will then be reflected into the UI, and the user will be presented with the data he had requested. Now let's talk about these three layers: the presentation layer, the business logic layer, and the data layer in the Android. So let's first take presentation layer. The presentation layer is the user layer. As I already said, that all the user interactions happen through this layer. This is the graphical interface that captures the user events and shows the results. It also performs operations such as verifying that there are no formatting errors in the user's data entry, and also helps in formatting data to be displayed in a certain way. So in Android, these operations are actually shared between the UI layer and the view model layer or the presenter layer based on which pattern we are following. The UI layer consists of activities and fragments in Android, and it captures the user events and helps in also displaying the changed or modified or the requested data. The view model layer formats our data in a way that UI shows them in a certain way and also verifies that the user's entries have the correct format. The core layer or the business logic layer or the domain layer is where all the rules of the business reside. This is the most stable layer, and this is the one that indicates what is happening in the software architecture which has been developed, and this is the least likely to change. The data layer is where the data is and where the data can be accessed. The data layer is further divided into the repository and the data source layer. The repository layer is the one that performs the logic of data access. For example, let's say the user has requested some new data. So repository could typically have logic that first it might go to a data source like a database and check if the data is in the local database and get the data that the user has requested back to him. But it also might be the case that the data that is kept in the database might be stale, or might be the case that the data that user has kind of requested might not be cached in the database, and the repository layer might have the logic to first get the data from the API, web API, and then store that or cache that in the local database and also return a copy back to the user for his perusal. The data source layer is where the implementation resides or the logic resides to access the data. For example, this layer in case of a web API implementation could have the logic surrounding retrofit to get the data from an external API. Or in case of database, it might be some logic related to SQL queries, which might get the data from the database. Now let's talk about the principles that one needs to follow in order to implement lean architecture. So broadly, these principles can be classified into two different categories. The first category is comprises of principles that we need to follow while designing classes. And the second category is the category of principles that we need to follow while designing components. So in case of classes, the main principles are the solid principles. In case of components, the principles are reuse, release, equivalence principle, common closure principle, common reuse principle, acyclic dependency principle, stable dependency principle, and stable abstraction principle. So let's talk about the solid principles first. So the first principle that I would like to talk about is the single responsibility principle. So what the single responsibility principle says is the class should only have one reason to change. Let's take an example. Suppose there's a class and a new requirement in finance office changes this class in certain way, but a new requirement in human resource department also changes this class in a different way. So in this case, what we see is this class gets changed because of changes in two different departments. So there are two different reasons for the class to change. Now, ideally, in such a scenario, if we encounter such a scenario in any of the classes that we currently have, what we should do is we should divide the class into two separate classes and such that each class has only one reason to change. What I mean by that is the area of or the content of the class which is changed by the finance office should be kept in a separate class, and the content of the class which changes due to the human resource department should be extracted into a separate class. The next what I'm going to talk about is the solid principle of open close principle. Here open means open for extension and closed means closed for modification. What this principle states is your design should be flexible enough so that it should be easier to add functionality to a class, but at the same time, you shouldn't need to modify any existing functionality. The reason the design should be done in this way is because usually you will have big inheritance hierarchies. And if you go and actually change something that was designed previously, it might cause a ripple effect and might cause you to change a whole lot of things. So it is required that initially itself you should design your classes in a way and keep extensibility in the future in your mind. So the way you take care of this is you ensure that each class has just one responsibility, and you hide the more stable classes behind interfaces so that they won't be affected when less stable classes have to change. The next solid principle I'm going to talk about is the Liskov substitution principle. People who are well versed with the concept of inheritance might have come across these principles while using inheritance. So this principle talks about substitutability. So what it says is in a computer program, if S is a subtype of T, then objects of type T may be replaced with objects of type S. What this means is if T is a base class and S is derived from it, then for every instance where T is used, S should be able to replace it without any issues. The next principle that we're going to talk about is interface segregation principle. What this principle says is no client should be forced to depend on method it does not use. So what usually happens is we define large interfaces sometimes in an application, and the clients that implement these interfaces might not be implementing all the methods, but are forced to inherit from this interface. So in such a case, what we should do is we should actually split the interfaces into smaller, more specific ones so that clients will only have to know about the methods that are of interest to them. Interface segregation principle is intended to keep a system decoupled and thus easier to refactor, change, and redeploy. The last of the solid principles that I'm going to talk about is the dependency inversion principle. So what it says is high level classes should not depend on low level classes, and both should actually depend on abstractions, that is interfaces. So what it says is whatever that is likely to change or the low level should always depend in the direction of should also always depend on something which is more stable and not the other way around. So that is abstraction should not depend on details, rather details should depend on abstractions. The idea behind this principle is that when you are designing the interaction between a high level module and a lower level one, the interaction should be thought of as an abstract interaction between them. Now, after going through these solid principles, I would like to talk about the component principles. So the first component principle that I would like to talk about is the reuse release equivalence principle. So what this principle says is whatever you release should be reusable as a cohesive unit, and it should not be a random collection of unrelated classes. Here, reuse refers to a group of reusable classes or modules, and release refers to publishing it with a version number. The next principle I would like to talk about for components is the common closure principle. It says that you shouldn't depend on component that has classes that you don't need. This is somewhat identical to the interface segregation principle in the classes. So what it suggests is you should split up your components so that the users don't have to depend on classes that they don't use. Now talking about the acyclic dependency principle, ADP says that you shouldn't have any dependency cycles in your project. For example, if you look at the diagram below, you see that component A is dependent on component B, B on C, and C back on A. So we can see that there is a dependency cycle here. So what might happen is when you change something in the component A, it might cause a change in component B, it might cause a change in component C, it might again cause a component in change in component A, then again in B, and it might end up in a cycle of changes, never ending cycle of changes. So the way this could be avoided is we could break the component into separate smaller subcomponents and hence break this cycle. The next principle we're going to talk about is the stable dependency principle. This principle says that dependencies should be in the direction of stability. So if you've seen the clean architecture diagram before, you would see that the source code dependencies were in the direction of stability, that is from low level to high level or from the details to policies. So it says that less stable components should depend on more stable components. Now, during designing of an architecture, you might have some volatile components, but you also need to make sure that you should not make stable components depend on unstable ones. The last component in in the component principles that I would like to discuss about is the stable abstraction principle. The stable abstraction principle says that the more stable a component is, the more abstract it should be. That is, the more abstract classes it should contain. The reason behind this is abstract classes are easier to extend. So this keeps stable components from becoming too rigid and hence make them extensible. So that's all what I had for this session. I would like to give credits to the following 5 resources from where I got the content for this session. So thank you everyone for being a part of this session.